Good afternoon. My slides are visible. Hello, am I audible? My slides are visible, right? Can you please unmute yourself and tell me that slides are visible or not? Okay, I assume my slides are visible. Yeah. So I'll start today. Welcome you all to this NPTEL course tutorial entitled as a study guide in organic retrosynthesis problem solving approach. And the course instructor of this course is Professor Samik Nanda from IIT Kharagpur, and I am Anirban Maiti. So, one of the TA for this course. So, today I'll discuss some functional group based retrosynthetic approaches. So, before that, this is the reminder. So those who did not attend the last class, so I have discussed about these syntones and synthetic equivalents. So if you have this, if you want to break this CC bond, so this is the carbon carbon bond, and if you want to break this is CC bond with heterolytic cleavage, then you will end up with this positive charge and negative charge. And this negative charge, so it is having this two electrons, so it can donate its electrons, so it is called donor synthon. And this positive charge, so it don't have any electron, rather it can accept the electron, so it is called acceptor synthon. So this donor synthon and acceptor synthon is this concept is mm, highly important for retrosynthetic analysis, because on the base of donor synthon and acceptor synthon you have to design the exact synthetic equivalent for each synthons. Right here here you can see that donor synthons, many donor synthons are there, and corresponding synthetic equivalents are also there. Okay, so in forward synthesis we have to use this synthetic equivalent, and then only we can get the corresponding donor synthon. As well as for acceptor synthon we are having various, here we can you can see various acceptor synthons are written, and corresponding to the synthetic equivalents are also written. So in particular forward synthesis we have to use this synthetic equivalent instead of this acceptor synthon. So this donor synthon and acceptor synthon, it is required for only retrosynthesis, but synthetic equivalents are required for forward synthesis. So this concept, I guess all of you knows. Now, so coming to today's problem, first problem. So this today we'll do some functional group interconversions based approach. So if you see this molecule, so this is our target, right? So this is our target molecule for retrosynthetic analysis. Okay, now we have to plan a suitable retrosynthetic analysis from this starting material. Here also we have written the starting material for your convenience. Now if you see the target molecule and starting material carefully, what you can observe, right? So you can see that, so the starting target molecule is have alpha beta unsaturated compound, right? And starting material also alpha beta unsaturated ketone, right? So both are alpha beta unsaturated ketone, but in target molecule there is one methyl substituent at beta carbon, right? So this methyl substituent is there at beta carbon. So we have to install that methyl substituent at beta carbon. How we can install? So simply we can add this methyl magnesium iodide, right? Grignard reagent in presence of copper iodide. But what will happen? You will get methyl, but this double bond will vanish, right? So we'll not get exact target molecule. So what else we can do? So there is one known reaction called bubbler oxidation, also known as bubbler Dauben oxidation. Okay. So what is happening in this oxidation? So you have to use Grignard reagents without copper iodide. Okay, without copper salt. So if you use copper salt, what will happen? That copper salt will make that Grignard reagent or alkyl lithium reagent softer. Okay, so that softer when the nucleophile becomes soft, that time it will adds to the beta carbon, because beta in alpha beta unsaturated ketone, beta carbon is more soft and this carbon in carbon is hard, right? So if you use copper salt in presence of Grignard, then this Grignard will add to the beta carbon. But if you add Grignard without copper salt, that time it will add to the hard carbon of that CO bond, right? So so if you come to the forward synthesis, how we can get this? So basically, if we add methyl lithium in diethyl ether solvent, so what will happen? 1 2 addition will take place. Okay, so that's this is 1 2 3 and this is 4. Okay, so without copper iodide or any copper salt, so 1 2 addition of this nucleophile will take place. So this will add to the C2 carbon, right? So 1 2 addition will take place. So, but if you add copper salt in presence of copper salt, any copper 1 salt, so that time what will happen? That time 1 4 addition will take place. Okay, because that will make nucleophile will become more soft. Okay, I hope you got some idea. So now, okay. Anyway, now we have to do we want to addition fast. So 1 2 addition will take place now. So you will get this. So this alcohol. So now if you see this alcohol, this is tertiary alcohol. Okay, so this alcohol is tertiary alcohol. Now some we if we want to do oxidation of alcohol, okay, oxidation of alcohol, we need to have primary alcohol or secondary alcohol. If we have primary alcohol, that time we will get aldehyde after oxidation, and if we have secondary alcohol after oxidation we will get ketone, right? But we if we have tertiary alcohol and if we wanted to do oxidation on tertiary alcohol, so we will not get any product. But interestingly, if you see this substrate, this is tertiary alcohol, but this is also allylic alcohol. Okay, so this is the olefin, and with respect to this olefin, this alcohol is allylic alcohol, right? So this is having some different reactivity in presence of oxidizing particular oxidizing agent. So in presence of chromium based oxidizing agent, chromium trioxide or PCC, if you treat that allylic alcohol, in those conditions, so you will get the oxidation product. But that oxidation will not happen at this carbon, rather it will take place at that carbon. Okay, so if you see, so in PCC 2 equivalent, so you are getting this alpha beta unsaturated ketone, but with transposition. Okay, so this carbonyl, this oxygen is coming to here. So transposition of this allylic alcohol, then oxidation further to get this carbonyl carbon. Okay, so I will show you details how this mechanism is happening actually. Okay, how this is happening in reality, right? So yeah, so this is the PCC. Okay, So this is the PCC, pyridinium chlorochromate. Okay, so this is the pyridinium salt of this chromate. Okay, chlorochromate. Okay, so this is the PCC, and this is your allylic alcohol, right? So first, what will happen? So first, this alcohol lone pair, so will attack on this chromium. Then this chlorine will leave. Okay, so this will come back and this fall back again, and this chlorine will leave, and you will get this type of intermediate. Okay, so this oxygen bond chromin and chromium, and this oxygen positive charge, it will have this positive charge. Now this chloride ion, this Cl minus, whatever it is living here, so this chloride ion will extract this proton, and it will release HCl gas. Just a minute. Yeah. So after this first step of this mechanism, so this type of intermediate will form. Now this whatever chloride ion is living here. So in the second step, that chloride ion will abstract this proton. Then this OH bond will break, and we will get this oxygen. So neutral oxygen here. So basically, this will leads to the elimination of HCl, and at the end you will get this chromate ester. Okay, so this is the ester with having chromium, so this is called chromate ester. Now this chromate ester with this pyridinium salt, right? So it will exist with pyridinium salt. Now what will happen? So basically now if you see, so one sigmatopic rearrangement will happen. So one, so if you say this oxygen is 1 and this chromium is 2 and this oxygen is 3, so this is 1 to 3, and this carbon is 1, this is 2, and this carbon is 3. So what will happen basically, 3 sigmatropic rearrangement will happen under heating. Okay, so this 3 sigmatropic rearrangement, if you clearly see the arrow, so this bond will migrate here and this CO bond will break, and this chromium oxygen, so this bond will migrate to this C3 carbon, right? So at the end you will get this chromate ester, right? So from this chromate ester to chromate ester to this chromate ester, you will get after 3 sigma tropic. So along with this double one isomerization. Okay, so basically this double one is coming, become this tricyclic now. Okay, so then this O minus, so this O minus will abstract proton, this proton, and this CH bond will break, and this O chromium will bond will break. So basically you will get this carbonyl oxidation of this at this center, and you will get this alpha beta unsaturated carbonyl compound, right? So you can see how this transposition is happening in presence of chromate ester. So this is known as bubbler oxidation, or sometimes it is called bubbler Doven oxidation. Okay, so but this is very interesting example. If you have allylic tertiary alcohol, okay, not any other alcohol, primary or secondary, in presence of tertiary allylic alcohol, only this transposition will happen, and you will get this rearranged oxidized product. Okay, so this is very interesting because in many natural product synthesis, this methodology some people use. Okay, so coming to the next retrosynthetic analysis. So if you see this molecule, so this is the same. Similarly, if you see, this is alpha carbon, this is beta carbon, and this is the alpha carbon, this is beta carbon, right? So in this retrosynthetic analysis, so this is our target molecule, right? Target molecule, and this is the starting material. Now in this target molecule, so we are having this beta substituent. So the beta substitution is vinyl group. Okay, so this vinyl group we are having at beta position, but in starting material we are not having any substitution at alpha or by beta position. So basically we have to add this vinyl group in the starting material, but we if you s- if you see these two structures, it is looking like that vinyl group is adding at this carbon, but it's not the case. It is having some rearrange mechanism. Okay, similar to previous slide, bubbler oxidation. If we think about, so in forward synthesis, basically we have to add this vinyl grignard. Okay, so vinyl grignard reagent. So without copper iodide, we have to add. Okay, so without any copper salt, what will happen? So this vinyl grignard will add to the uh, carbon in carbon, right? Right. So this is 1 2 addition will take place. So 1 2, this is the number 3 carbon and this is the 4 carbon. Okay, fourth carbon. So without copper iodide, what will happen? So this vinyl grignard is become hard now, and this will add to the hard carbon in center, right? So if you add copper salt, then 1 4 addition will take place. Okay, so this time it is normal 1 2 addition, and what will happen, you will get the 1 2 addition product, right? So phenylated alcohol. Okay, now what will happen? So basically now this is again allylic alcohol. Okay, with respect to this vinyl group as well as this vinyl group, so this is an allylic alcohol. So what will happen, like previously, if we treat this allylic alcohol with oxidizing chromium based oxidizing reagent, so this transposition of this allylic alcohol will happen. So this alcohol actually it will, so this double bond will migrate here, so this bond will migrate here, and this alcohol transposition will take place. Okay, then this carbon will have alcohol, okay, in presence of PCC. So and two equivalent, so another equivalent of PCC will do this alcohol C alcohol oxidation. Okay, so basically you will get this product, right? So this is the another example of this bubbler oxidation. Okay, so very interesting example for bubbler oxidation. Just a minute. Yeah, so now coming to the next slide. Next slide, we have another molecule for retrosynthetic analysis. So this molecule we have, this is our target molecule. Just a second. So this is our target molecule, right? So target molecule, if you see, so what is this? It is having this 1 2 diol. So this 1 2 diol, one is primary alcohol, this is tertiary alcohol, right? So how we can think the retrosynthetic analysis for these molecules. This is very simple molecule. So functional group interconversion based approach. So basically we can think about that this we can get from this epoxide, because if we add hydroxide ion, okay, hydroxide as a NaOH or LiOH in, so that hydroxide based ring opening of this epoxide will give this 1 2 diol, right? So this so epoxide how we can get, so this epoxide we can get from this carbonyl carbon. Okay, so I guess I will maybe you know knows or I don't know. So there is one methodology known as name reaction, basically Kore-Tchaikovsky reaction. So sulfoxonium or sulfonium ylide based reagent, so that if you treat any carbonyl compound with sulfonium or sulfoxonium based ylide, you will directly get this epoxide. Okay, Kore-Tchaikovsky reaction. So this methodology we can apply here. Now this carbonyl carbon we can get from this alcohol by oxidation, right? So in forward synthesis, if we see the forward synthesis, so what will happen? So in forward synthesis, if we have this secondary alcohol, so secondary alcohol, if we do oxidation, so we can use many oxidizing reagents like PCC, PDC, or IBX. Here we use DMP and DCM as a solvent. Okay, so if we use DMP in DCM, so we will get the oxidation of the secondary alcohol and we will get this carbonyl compound, right? Now this is the main reaction here, Korey-Chakovsky reaction. So if we have this methyl, this is called sulfoxonium ylide. Okay, there are two ylides, so this is not ylide. If we treat this compound with base sodium hydride, that time ylide will generate. Okay, so now I will show another reagent. So this is sulfur, methyl Me, and this is CH3 carbon, CH2, and another proton. Okay, so this is, and the sulfur will bear positive charge. Okay, so this is the trimethyl sulfur, right? Trimethyl sulfur. If you treat this compound with base like sodium hydride, so that base will take this proton, right? So because this is more acidic proton, so this base will take this proton and it will generate basically this CH2 minus. Okay, so this CH2 minus, so CH2 minus and S plus, so minus plus in adjacent atom, so that is known as ylide, right? So this is the sulfur ylide. So now this is sulfonium base ylide. But if you have this sulfur double bond oxygen, okay, see, if you have this oxidized sulfur, that time we will call sulfoxonium ylide. Okay, so basically again, if we treat this compound with sodium hydride, so one of the proton base will sodium hydride will take one of the proton, right? So base will take this proton and this sulfoxonium ylide will form. Now this CH2 minus, so CH2 minus will attack to this carbonyl carbon and it will generate basically CH2 minus and SO2Me, right? SOMe2. So this CH2 minus, okay, CH2 minus will add to this carbonyl carbon and this CO bond will append so to give O minus. So basically you will get O minus and this is CH2. This is the CH2 and this is the S double one O and Me2, right? So what will happen in the next step? So this will get, after addition of this carbon and you will get this intermediate, right? Now this O minus will add to this carbon and this CS bond will break. Okay, and you will get this epoxide. You can think, you can imagine, right? And what will be side product? Side product will be the Me2SO, right? So side product is dimethyl sulfoxide, right? So this is the side product, DMSO, dimethyl sulfoxide. So you will get this epoxide. So this name reaction, so this is a very famous reagent for this epoxidation of carbonyl compound. Generally we know how to carry out epoxidation on double one, right? Olefin. But if someone asks to do epoxidation uh, in carbonyl compound, then how we'll do? So you have to apply this sulfonium or sulfoxynium chemistry. So by the help of this Korey-Chaykovsky reaction condition, you can get easily the epoxide product. Okay. Now what will be the next? So this epoxide we got. So what will be the next? So after getting this epoxide, basically we have to open this epoxide. Okay. So to get this diol, because this is our target. So and this is the epoxide. Okay. So if we, so now this epoxide ring opening we can do via two process. One is this is the base mediated, and the second one is acid catalyzed. Okay, base, in basic condition what will happen? So OH minus will act, OH minus that will directly open this epoxide, and you will get this O minus and alcohol, and O minus will take proton from water, so H plus from water, and you will get the diol, right? So this is the base catalyzed mechanism, and if you have base mediated mechanism, not catalyzed, and if you want to carry out acid mediated epoxide ring opening, that time you have to treat with OH plus, right? So H plus, so basically that H plus, so what will happen, it H plus, so this oxygen lone pair will catch first H plus. So now it will become this O plus, right? So after getting catching this H plus, it will become this OH and this O plus, right? And now water will attack. Okay, water will attack to this carbon, and then ring opening. So you'll get this OH2, and then H plus, elimination of one H plus, you'll get this 1,2 diol. Okay, so this is the mechanism. So you can see how we can get diol from epoxide, and epoxide how we can get from Korey-Chaykovsky condition from a ketone, right? So very interesting example. Coming to the next problem. So the next retrosynthetic analysis. So we'll here we will see, we'll do the retrosynthetic analysis for same molecule. Okay, but not from epoxide. Uh, yeah, not from epoxide. How we can think about another retrosynthetic analysis? So this is the target molecule, right? TM. So how we can get? So this target molecule we can get from this olefin, right? So this is the 1,2 diol we can think. So this is carbon 1, this is carbon 2, and this is 1,2 diol. So this 1,2 diol we can get from this olefin, right? So by 1,2 dihydroxylation condition. So this olefin now from where we can get? So very interestingly, this olefin you can get from carbonyl compound. This carbonyl compound. So now this carbonyl compound, if you do the Wittig reaction, okay, so methyl Wittig reaction, we will get easily this olefin. Now similarly, this carbonyl carbon, this carbonyl compound, how we can get? So we can get from the corresponding alcohol via oxidation. Okay, so if you see the difference between previous retrosynthetic analysis for this molecule, the major difference is these two steps, first this one and this one. So basically, previously we were thinking that this diol could be obtained from epoxide, and that epoxide we could get from this carbonyl compound, but here this intermediate is different. Here we are planning that 1,2 diol we could get from this olefin, this double one, and this olefin we could get from this carbonyl compound, and this carbonyl compound similarly we could get from this secondary alcohol via oxidation, right? So in the forward synthesis, similarly we have taken this secondary alcohol, and if we treat with this DMP oxidizing agent in DCM, what you will get? So we will get basically this oxidized product. So only one hydroxy group is there, so you'll get this predominantly this carbonyl compound, okay, cyclohexanone. Now this compound, if we treat with, so this is the Wittig reaction condition, okay. So basically if we have this methyl Wittig salt, so this is the Wittig salt. Now we have to generate Wittig elide. So if you see, this is the CH2. So this is the Wittig salt I am drawing, PPC plus and Br minus, right? Now, first what will happen? We are using this THF is solvent, tetrahydrofuran, and potassium tertiary butoxide. So the pK value of potassium tertiary butoxide is around 17, I guess 17. Yeah. So what will happen? This oxide. So this will abstract this proton. Okay. So this potassium tertiary butoxide will abstract this proton, and you will get this elide. Okay, so this CH2 minus you will get, and this is the elide. Okay, so this Wittig salt to Wittig elide we generated here. Now so this elide will attack to this carbonyl carbon, and at the end it will generate the oxaphosphetane intermediate, right? So all of you know Wittig reaction how works. So basically you will get, so this oxaphosphetane intermediate, right? Now decomposition of this oxaphosphetane intermediate will leads to the olefin product, right? Because this PPC oxide will form, so this 2 plus 2 in retro of this 2 plus 2, so it will generate this olefin, right? So this Wittig reaction, it's after doing this Wittig reaction we will get this olefin. Now from olefin how we can get this 1,2 diol, so very common. So there are very common oxidizing agents known as osmium tetroxide. If we treat this olefin with osmium tetroxide reagent, we will easily get this 1,2 diol, right? Very common. So you can see for same molecule, so from same target molecule we can have different retrosynthetic plan, okay. So depending upon the reagent conditions or functional group presence in your molecule, we can plan different retrosynthetic plan, because sometimes what will happen, so we'll not have all the chemicals in our laboratory, okay. So if we have different retrosynthetic plan according to our source we are having in our lab, so we can carry out the desired transformation to get the target molecule, right? So this is the benefit of having different retrosynthetic analysis. Okay, now after this we will come to the different example, okay. So this is the another example. If you see this molecule, what is this molecule exactly having? So this molecule is basically, if you see, this is an bicyclic compound, fuse compound, 6 fuse compound, and having this olefin and this trans 1,2 dihydroxy compound, okay, this trans 1,2 dihydroxy compound. So this 1,2 dihydroxy compound trans how we can get in trans? There is only one way. If you have epoxide, okay, if you have epoxide, then epoxide ring opening could give this one to trans diol, right? So this could be obtained from this epoxide, so via ring opening of epoxide, okay. So ring opening of epoxide, we can get this 1,2 diol, right? Now how we can get this epoxide? So it is epoxide basically we could get from the olefin, corresponding olefin. So this is the triene. Okay, from triene. So if you see there are three double bonds. Okay, and this olefin, if you see this is tetracyclic, so it is more electron rich. So by utilizing this concept of this more electron rich double bond epoxidation, we can you can oxidize this olefin exclusively. Okay, so now this olefin triene, from where we can get basically from this naphthalene, okay, via Bar's reduction condition. Okay, so we can think about this Bar's reduction of this aromatic naphthalene compound to get this triene. Okay, so now forward synthesis. So forward synthesis, how we can carry out this retrosynthetic plan in forward direction. Okay, so basically we have, if we are having this aromatic naphthalene, so then first step is Barch reduction. So this is the Barch reduction condition, having using lithium, two equivalent we have to use because two rings are there, two aromatic rings are there, so we need two equivalent, more than two equivalent to complete this TGR conversion. Okay, so first lithium in liquid ammonia, in tertiary butanol and diethyl ether. Okay, so single electron mediated this Bar's reduction will give this triene. I am not going to details of this Bar's reduction. You can find easily in your textbook. Okay, so this not very easy name reaction, common name reaction. So after happening this Bar's reduction, so we will get this triene. Now if you see this olefin and this olefin, those are disubstituted, right? Now this middle one is tetrasubstituted. So easily we can do the epoxidation of this olefin by using one equivalent of one epoxidizing reagent, right? So do if we treat with one equivalent of MCPVA, so metachloroparbenzoic acid is one of the epoxidizing agent. So basically we will get this epoxide, right? Now so the next step is we have to we have to open the ring of this epoxide, so that we can get this trans 1,2 diol, right? So basically if we treat with this formic acid in acid catalyzed epoxide ring opening condition, we can get this intermediate format. So this format type of intermediate, basically how we'll get, so this acid formic acid mean H plus and so OCHO, right? So this is the formic acid. So in ionic form it will be looking like this. So first this oxygen will catch this H plus, and this O minus will add to the epoxide carbon. Okay, so basically you will get this OH and OCHO format. Now in sodium bicarbonate workup condition, so again the hydrolysis of this format will happen and you will get this OH here. Okay, so this OH, so this is a mechanism. So in formic acid mediated epoxide ring opening, so through this format intermediate you will get this 1,2 diol, not so 1,2 diol, and the stereochemistry, the relative stereochemistry is trans. Okay, so this is the major thing, okay, in this conversion. Now the next retrosynthetic analysis. Okay, so what is happening here? So basically if we have this diol compound. Okay, so if we are having this diol compound, so how we can get, so we can have this starting material having olefin here. Okay, so retrosynthetic analysis is this. So target molecule already given to you, and also starting material also given to you. Now this is the retrosynthetic plan. Okay, so this target material, how we can get from this starting material. So forward synthesis, so we'll have this starting molecule or starting material. So now what reaction we have to carry out? So we have to use this hydrolactonization concept. Okay, this reaction condition. Professor Samik Nanda also in past few lectures he has discussed about this hydrolactonization mediated some retrosynthetic analysis. Okay, so this hydrolactonization or halolactonization is very interesting because of in some retrosynthetic plan this will help you to get your desired target molecule. Okay, so this hydrolactonization, basically what will happen, some lactone will form and iodine will form. Basically if you have this olefin, so first in iodine sodium bicarbonate condition you will have this bridge iodinium ion, right? So bridge iodinium ion will have, right? And in sodium bicarbonate condition, this carboxylic acid. Okay, so the sodium bicarbonate will abstract the proton of carboxylic acid, and it will form this carboxylate anion, right? So this carboxylate anion will open this iodinium bridge iodinium intermediate. Okay, and it will form how many ring? So one, two, three, four, five, and this oxygen six-member ring with having this iodine. Okay, so this is very interesting example. So in this hydrolactonation you will have this six-member lactone with iodine. Okay, now in target molecule we don't have any iodine, right? So basically first we have to do the elimination of this iodine. Okay, so reductive elimination. So in radical so you have to use this radical process, radical method. So AIBN and NB3SNH. So all of you know the mechanism how to do reductive elimination of this halides, right? So you'll get this CH2. Okay, CH2 at this position. Now only one step is remaining to get your target molecule. Basically if you reduce this six-member lactone, okay, reduce, so you will get this CH2OH here and CHOH here, right? So basically you will get your desired molecule. So if you reduce this six-member lactone with lithium aluminum hydride, you will get this diol. Okay, your target molecule. So this is very interesting example, you can say. Yeah, so you just see how this conversion is happening. And just a minute. So okay, so now coming to the next problem. Okay, so next problem is very interesting molecule. If you see in this slide, so both and target molecule and starting material are given. Okay, just a minute. Yeah, so my slides are visible. Can you unmute and tell my slides are visible or not? Okay, So if you see this target molecule and this is the starting material, so both target molecule and starting material are given in your retrosynthetic analysis. Okay, so if you see this target molecule, it is having this 7 member ring. So this is the 7 member ring, and the next one is 5 member ring. Okay, 7 5 fuse lactone. Okay, now if you see this target starting molecule, so it is a bicyclic compound having this 1 2 3 2 true. Okay, 3 2 2 bicyclic compound. Okay, so you can see how we can convert this bicyclic compound to your corresponding target molecule. Okay, so this is the 3 2 2 target bicyclic compound, bicyclo compound, and this is the 7 5 fuse ring. Okay, so very interesting example conversion, how you can do the conversion of this starting material to get this target molecule. Okay, so in forward synthesis, basically we'll see the forward synthesis first. So in forward synthesis, we are having this. Basically, if you observe this starting molecule, starting material, it is having this carbonyl compound. Okay, carbonyl carbon here and this carbonyl carbon here. Okay, two ketones are there. Okay, so two ketones are present in this molecule. So basically, if we think about some Bayer vinegar oxidation type of reaction, okay, so MCPBA mediated or this paracetic acid mediated Bayer vinegar oxidation, what will happen? Bayer vinegar oxidation will happen. Two carbonyl carbon are there, so both carbonyl carbon will undergo Bayer vinegar oxidation. Okay, so this carbonyl carbon will give predominantly this acetate. Okay, so this acetate will give. Okay, now the difference will come here. Okay, so in Bayer vinegar oxidation, if you see this carbonyl carbon, so there is two carbon. Okay, so two competitive carbon in terms of migratory aptitude. So this CH2 is secondary. Okay, this is the secondary carbon, and this is the tertiary carbon. Okay, so now the migratory aptitude of this tertiary carbon is more than this 2-degree carbon. Okay, so if you see when this tertiary carbon will migrate, so you will get this lactone, right? So this lactone, so Bayer vinegar oxidation of this carbonyl group along with this carbon migration will give this lactone, right? Whereas the Bayer vinegar oxidation along with this secondary carbon migration will give this lactone, right? So now, as you know, the tertiary carbon migratory aptitude is more than secondary carbon migratory aptitude. Okay, so that's why you will get predominantly. So if you see the yield of this reaction, see this is 85% and this is 15%. So almost you are getting this product as a major. Okay, so your uh, desired product you are getting as a major amount, and this is undesired product, not undesired you can say. So this is the another product you are getting in less amount. Okay, so now with this product we will move ahead and we'll see what we can do with this product. So this major product we are having, and if we do the hydrolysis of ester. Okay, so this acetate hydrolysis along with this uh, lactone, if we do hydrolysis in presence of potassium hydroxide in methanol, so what will happen? Basically we'll get this OH here and this acetic acid, and in this lactone we'll have this acetic acid, carboxylic acid at this side, and this alcohol. Okay, secondary alcohol. Now if you redraw this molecule, so basically s- this is nothing but this 7 member lactone with all stereochemistry. If you see the stereochemistry of methyl, this hydroxy, and this acetic acid functionality, all are in same stereochemistry. Okay, like all are beta. So in 7 member ring, all are having this uh, beta relative stereochemistry, right? So if you see how we can convert this bicyclic compound to a seven member ring, now the job is almost done. So only we have to do lactonization with this hydroxy group and this acid, carboxylic acid side chain. Okay, so if we do the lactonization, so now our target molecule we can get easily. Okay, so we have our next step is to do the mineral acid treatment to get this lactonization product and this 5 member lactone. So this is our target molecule. So very interesting example you can imagine of this retrosynthetic plant. So this target molecule is 7,5 fuse ring with a lactone, and the starting material is 3,2,2 bicyclic compound. So how you can think about this conversion? So very interesting amazing example. So first you have to do bialbilic oxidation, then so you will get lactone, and if you hydrolysis lactone, basically this bridge will eliminate, so you will get seven member ring. Okay, so this seven member ring, after getting this, if we do lactonation again with this acid and alcohol, we will get this so this, we will get this compound, right? Very interesting. So now coming to our next problem. So next problem is also an interesting example. So if you see this molecule, so this is a, the name of this reaction molecule is plus, so this is plus trans 3 hydroxy pipecolic acid. So if you see this molecules is alcohol and carboxylic acid stereochemistry, it is trans. Okay, so these two stereochemistry are trans. Now how we can think about the retrosynthetic plant, from where we can get this molecule? So first in forward synthesis, so this is our target molecule. So this could be, this we could get from this molecule via, so this molecule via functional group interconversion. Okay, so FGI, so FGI at here. Okay, so basically if we, and this is a secondary alcohol, and if we do oxidation, we will get this carboxylic acid, right? So now this compound from where we can get, so this could be obtained from this halide. Okay, corresponding halide via this CN bond disconnection approach. Okay, if we think about this CN bond disconnection approach, by simple SN2 reaction, we will get this six member ring. Okay, six member ring. Now, so this cyclization precursor, so this, if we do this molecule, if we do cyclization, you will get this six member piperidine ring, right? Now the cyclization precursor from where we can get, so we can get from this alcohol. Okay, so protected alcohol. So this Pg1, Pg2, Pg3 are basically nothing but protecting group 1, protecting group 2, protecting group 3. So three different protecting groups. Now this molecule, so this molecule we could get from this compound, right? So this basically from alcohol to amine transformation, functional group transformation. Now this secondary alcohol we could get from this olefin via 1 to dihydroxylation. Okay, dihydroxylation of this olefin will get this compound. Now this olefin how we could get, this olefin how we could get, so we could get from this aldehyde via Wittig reaction. Okay, Wittig reaction with other side chain, we will get that olefin, right? So this is our retrosynthetic plan for this piperidine derive this trans molecule. Okay, this trans 3 hydroxypipicolic acid. So this is our retrosynthetic plan. Now forward synthesis. So forward synthesis is more interesting. Okay, so basically if we are having this 1 2 3 4 butane diol. Okay, so this molecule is 1 4 butanediol, and this is symmetric molecule, right? So basically if we treat this molecule with one equivalent of PMB chloride, so what will happen? Only one alcohol will get protect. Okay, so in presence of sodium hydride and PMB chloride of one equivalent, we will get one hydroxy protected PMB protected hydroxy compound, right? So one hydroxy will get protection, PMB protection, and another hydroxy group, free hydroxy group, will oxidize by using PCC. So pyridinium chlorochromate based oxidation will get aldehyde another side. Okay, so basically we will have OPMB and another side we will have aldehyde, right? So this is the compound. So now this aldehyde, if you see, so this aldehyde we are treating with this epoxide, Wittig reagent. Okay, so this is the Wittig elide. So already Wittig elide we are having, and this aldehyde, if we treat with Wittig elide in DCM solvent under reflux condition, we will get the corresponding olefin product, right? So this is the corresponding olefin product. Now, after having this, so this is the alpha beta, sorry. So this is the alpha beta unsaturated ester, right? So is alpha beta unsaturated ester, if we treat with dival H, okay, dival H, what will happen? So basically it will reduce this ester to alcohol. So you will get this alcohol, right? So this is now allylic alcohol. Okay, that is okay. So now if you see here, we I have written that after dival H treatment we have to use Rochelle salt for workup. Okay, so most of you don't know when you are doing dival H reduction. Okay, so in dival H reduction, so basically it is diisobutyl aluminum hydride, right? So it is aluminum based hydride reagent, right? So isobutyl. So aluminum based hydride agent, diisobutyl aluminum hydride. So what is happened? So this hydride, so this reduction of ester by using dival H, so you'll get allylic alcohol as your product. But what will happen to this aluminum based this aluminum reagent? So basically, after the reaction, it will form a emulsion type of uh, solution. Okay, so emulsion, it will form aluminum will form emulsion. Okay, that this reagent will form emulsion in your reaction, uh, in your RB. Okay, round bottom flask, in your reaction mixture basically. Okay, so that emulsion is very separate, so it is difficult to separate your product from that emulsion. Okay, so for that purpose you need to use some compound, so that that emulsion you can destroy. Okay, so this Rochelle salt is basically sodium potassium tartarate. So what will happen, that Rochelle salt sodium potassium tartarate, that will destroy the emulsion. Okay, and it will give you two clear solutions of water and your organic solvent. Okay, and from that two clear solution you can easily separate uh, your this product from the reaction mixture easily. Okay, so that is why when you are using dival H in reduction, you have to use Rochelle salt during workup. So Rochelle salt will break the emulsions of aluminum. Okay, and you will get the clear solutions, and then you can easily separate your molecule. So okay, now after getting this allylic alcohol, So what is the next? Next we have to do dihydroxylation, 1,2 dihydroxylation. So this we are using ADMX alpha. So ADMX alpha conditions we are using. So that is mean Sharplex asymmetric dihydroxylation, right? So osmium tetroxide DHQ dimer, DHQ2 fall. So this is the ligand, and K3 efficient 6, K2CO3, and this sulfonamide in tertiary butanol water. So we will get in this admix alpha condition. So we will get this 1,2 diol, cis diol. So with 92% enantiomeric excess. Okay. So this triol we are having now, 1, 2, 3 triol we are having. So then we have to protect this 1,3 diol. Okay, 1,3 diol. We have to protect with this phenyl orthoformate to get this 1,3 diol protected product, and this C2 this C2 alcohol free. Okay, this C2 alcohol now we have to do some functional group interconversions. Okay, so basically this C2 alcohol, so this alcohol will make fast, will convert this alcohol to living group by treating with OM, methyl chloride and triethylamine. First we will have this OMS, right? So in first step we will have OMS. Now we will treat the COMS to sodium azide. Okay, so sodium azide, so nucleophilic displacement will happen and it will give this azide, right? So what is next? Next is in DDQ mediated deprotection of PMB, OPMB to give this OH, and then next we have to reduce this next we have to convert this alcohol to again another living group, same living group we use here. So OMS, okay, in presence of methyl chloride and triethylamine, will we make this alcohol to living group, and then in hydrogenation condition, this azide N3 will reduce to give this NH2, right? So NH2 will form, and this NH2 what will happen, that NH2 in situ it will add to this carbon, and SN2 reaction will happen. Okay, so you will get 6-member piperidine ring in situ. Okay, so this is very interesting. So in same condition, in same hydrogenation condition, first azide to amine will form, and this amine will undergo nucleophilic substitution reaction to give this piperidine ring. So this is the molecule now. So after that we have to protect this amine with Bock anhydride to get this N protected amine, right? Sorry, Bock protected amine, secondary amine. Then if we treat with so one equivalent of tributps chloride and imidazole as a base in DCM solvent, what will happen? So this is the secondary alcohol and this is the primary alcohol. Two alcohols are there, but secondary alcohol is sterically not available, right? So primary alcohol is more available sterically, so it is more sterically free. So that's why what will happen. So this one equivalent TBDPS chloride, so first this alcohol will protect to get OTBDPS. Okay, now after having this compound, so we have to protect another this alcohol with mom group. Okay, and we will get this O mom. So in presence of mom chloride and diisopropyl ethylamine, so we'll get this diprotected alcohol. Okay, so three different protecting groups are here if you see. So this is NBOC, this is OTBDPS, and OMOM. Okay, now if we treat this compound with azepyridine, so azepyridine is fluoride ion. Basically it is fluoride ion it will give, and it fluoride ion, and OTBDPS is O silyl tarbutyl diphenyl, right? So this fluoride ion is will attack to silicon, and silicon oxygen bond will break, and you will get this OH. So deprotection of OTBDPS. So if you have silyl based protecting groups, and if you treat with some fluoride based reagents, so you will get deprotection of that silyl base protecting group. Okay, so after getting this CH2OH, we have to do this oxidation of this primary alcohol. Okay, this condition to get this carboxylic acid, and then deprotection of N block in 6 normal HCl. So in acidic condition, so we'll get this Bach deprotected product as well as this primary alcohol oxidized product, this carboxylic acid. So this is our target molecule. Okay, so this was our target molecule, and you can see how easily we can get this target molecule from a known 1,4. So this from this known 1,4 dibutane. Okay, so after several transformation we can get easily our target molecule, right? So now coming to our next problem. So next problem is also interesting. So if you are, so this is the molecule. So if you see this molecule, so this is having this 5 member lactone. So 5 member is gamma lactone. Also this CH2OH, okay, and both alcohol are protected with different protecting group, trityl protection and OBN, benzyl protection. Okay, so how we can think about the retrosynthetic analysis. So basically this is uh yeah, so this is our target molecule. So this target molecule, how, so first functional group interconversion. Functional group interconversion, so basically lactone formation. Okay, so this lactone formation from this alcohol and acid. Now this acid, how we can get, so we can get from this olefin. Okay, so olefin, from that olefin we can oxidize that carbon, and we can get this carboxylic acid. And this olefin, how we can get from epoxide. Okay, so epoxide and epoxide ring opening could give this olefin. Okay, so now coming to our forward synthesis. So forward synthesis is the, we will see the forward synthesis for this plan. And now this epoxide we can get from olefin by epoxidation. Okay, so coming to forward synthesis. So if you just see the forward synthesis, so this is the starting molecule. Okay, so this is the starting molecule. So you, we have to treat this with trityl chloride, one equivalent of trityl chloride, one equivalent of chloride in triethylamine in DCM. So one of the alcohol will get protected with trityl group. So let's say this alcohol is protected with O trityl. Then, so then now see it is an allylic alcohol. Okay, so olefin is, and this alcohol. So this is allylic alcohol. Okay, so this epoxidation, so Sharpless epoxidation condition plus date and titanium isopropoxide in presence of tert-butyl hydroperoxide epoxidizing agent. So we'll get this epoxide with 96% of enantiomeric excess. So this is the condition of Sharpless epoxidation condition. Okay, right? So after getting this epoxide, so another alcohol, that alcohol will protect with benzyl. Okay, so we'll get this OBN, right? OBN. Now we have to open this epoxide by using this acetylide. So this C minus and Li plus, right? So acetylide mediated epoxide ring opening. So what will happen? So this epoxide will open, and you will get this tertiary alcohol along with this alkyne. Okay, now we need to get olefin here. Okay, double one. So this olefin, how we can get? So from alkyne to alkene, by using a linear catalyst in presence of quinoline and hydrogen. Okay, so this linear catalyst mediated alkyne to alkene transformation will get this olefin, and then hydroboration oxidation to get this primary alcohol, right? So now primary alcohol we are having, so now we have to oxidize this center. Okay, so this primary alcohol we have to oxidize to get carboxylic acid. So if you treat with PCC, so if you treat with oxidizing agent PCC this alcohol, so basically this alcohol will give aldehyde, and that aldehyde will form in situ lactol. Okay, so this lactol, so first lactol will form, and in presence of excess PCC, so oxidation of lactol will happen. Okay, so oxidation of lactol will happen, and you will get this uh, this lactone. Okay, gamma lactone. So this is our target molecule, right? So you can get this target molecule from your starting molecule after after few transformation. Okay, so coming to the next example. Yeah, next example. Okay, just a minute. So this retrosynthetic analysis. So if you see this molecule, so the two carbonyl groups are there. So this one, two, three positions I am counting. So carbonyl group positions are like 1 4 dicarbonyl compounds. Okay, so now in retrosynthetic plan, if we plan about the retrosynthetic analysis, so we can think about this CC1 disconnection approach, right? So this CC1 disconnection. So this CC1 disconnection approach, if we think, so what will happen? Basically, so what will be the corresponding syntones? So let's say it is having positive charge, it is having negative charge, right? So positive charge we can easily generate at this. So if you see, if you count this carbonyl compound, and this positive charge is coming at beta position, alpha and beta position. Okay, and this negative charge is at carbonyl carbon. Okay, so positive charge, if you are thinking about alpha beta positive charge, so we can easily think about alpha beta unsaturated carbonyl compound, right? So this alpha beta unsaturated carbonyl compound, so if you thinking about this acceptor syntone, so it could be derived from this alpha beta unsaturated compound, so this will be the synthetic equivalent, right? And what about this donor syntone? So donor syntone, so carbonyl carbon bearing negative charge, that means we have to think about ampulang chemistry. Okay, so reversal of polarity, so we can think about two different parts. So true reversal of polarity, ampulang chemistry of carbonyl carbon, we can think about this 1,3 diethane based chemistry, because this proton is highly acidic, and any base if you treat this. So this pK value is 31, right? So this is pK of this carbon proton is 31. So if you treat with NBT lithium, you'll easily generate carbon here. Okay. So another possibility is there. You can think about nitromethane base reagents. Okay. So pH. So you need some pH here. Okay, and you can easily generate carbon here. Okay. So nitromethane generally pK value is around 10 to 13. Okay, depends depending upon the substituents at this methyl position. Okay, so this is the pK value now. So basically, so this will be the two synthetic equivalents for acceptor synthon, sorry, donor synthon. So basically we are in this retrosynthetic plan we will use this synthetic equivalent. uh, so NAP reaction mediated. So basically we can think about these two synthetic equivalents. So basically first what will happen, one for addition will take place and you will get this nitromethane, and NAP reaction if you do you will get this one for dicarbonyl compounds. So in forward synthesis basically what will happen, in forward synthesis first what will happen. So this is a methyl vinyl ketone, right? MVK. Now nitromethane will addition. Okay, nitromethane addition will take place. So basically, if you treat with any base like DBU, so this carbon will generate. Right. So now one for addition will take place. Okay, one for addition will take place, and you will get this compound, right? So this compound you will get if you treat with DBU. Now after getting this nitro derivative, so what we have to do, we need to get this carbonyl compound here, carbonyl ketone here. Okay, so basically if we need to treat with this nitro with NAP reaction conditions. So you can treat with TiCl3. So this is reductive method, TiCl3. So we can easily convert this nitro to carbonyl compound. Okay, so this is easy going conversion, and we can get this 1,4 dicarbonyl compounds. Okay, so also 1,3 diethane addition also we can think about, 1,3 diethane addition also we can think about. So if we can think about 1,3 diethane addition to this methyl vinyl ketone, so basically 1,3 diethane, right? Okay, this is a phenyl, and this is minus, right? So this minus will add to this carbon, and this will happen. Okay, yeah. So for on for addition of this 1,3 diethane, you need to use HMPA. So this I discussed earlier, I guess in lectures, in tutorials 3, week 3 tutorials, I have discussed the role of HMPA in 1,3 diethane 1,4 addition. Okay, so basically HMPA is a hexamethyl phosphoramide. Okay, so P double one O N N N. So hexamethyl, each nitrogen is having two methyls. So hex 1, 2, 3, 4, 5, 6, total 6 methyls. So hexamethyl phosphoramide. So this is HMPA. So HMPA will so basically it will, so this carbanion will have some its counter cation, okay, so like say Li plus, okay, so Li plus. So basically this nitrogen will coordinate to Li plus and it will make this carboanion and carbocation. So this carboanion and Li plus separate, okay, so basically you will see the free carboanion, okay, and the free carboanion is can add to this alpha beta unsaturated ketone in 1,4 fashion, okay. So this 1,4 addition will take place in presence of HMPA and will generate this intermediate, right? So now, so this is the protected, basically this is the protected 1,3 diethane derivative. So so by this NAP reaction condition we can easily get this nitro derivative, and we can so from nitro to this one for dicarbonyl compound we could get by performing NAP reaction conditions like TiCl3 or DBU oxygen. Okay, so this is the retrosynthetic analysis for this molecule. Now another example we'll see. So another quick example we'll see. Yeah. So this molecule, okay. So this molecule, if you see, this molecule is a 6,5 fuse ring, okay, 6,5 fuse ring, having this CH2NH2. And so how we can think about retrosynthetic analysis? So basically functional group interconversions to get this 6,5 fuse ring, and then so basically this functional group interconversion at this center, okay, so this aldehyde to amine via reductive amination condition we could get. Now this molecule, this 6,5 fuse, how we can get? So this basically ring formation of this ring formation. So this name reaction is known as conia in reaction, okay, conia in cyclization basically. So basically if you treat with any Lewis acid like copper salt, or if you treat under heating condition, any heating condition, you will get this conversation, okay. And this aldehyde and this olefin, how we can get? Basically if you have this uh, 1,4 alpha beta unsaturated aldehyde, and if you add uh, this allyl magnesium bromide, so you will get this is a homoallyl, right? So you will get this compound, right? Now this conia in reaction, how it happens, okay, how it works? So basically under heating or Lewis acid conditions, so this aldehyde, so aldehyde will it will be in equilibrium with this enol, okay. So this enol, now this enol, what will happen, this in cyclization will happen. So 1,5 hydrogen shift or in cyclization will happen. So basically this OH bond will break and this enol will add to this olefin, and this will take this proton, okay, this hydrogen, okay, not proton, hydrogen. So this is a concerted mechanism, not ionic mechanism. So you will get this compound. So enolization followed by 1,5. So first in heating condition enolization will take place, and then 1,5 hydrogen shift will take place. Okay, so you will get this you will get this cyclism and this so you can see how this 6 5 fuse ring is you are getting easily. Okay, now from how you can convert this aldehyde to amine. Okay, so basically if you treat this aldehyde, yeah, if you treat this aldehyde with some benzyl amine, right? So benzyl amine, so what will happen, so this aldehyde will make imine NBN. So suppose this is the R. Okay, so this, then if you reduce it with hydrogen palladium carbon. Okay, so why we can use sodium borohydride as well. Sodium borohydride, what will happen, only imine reduction will happen, but we need to deprotect this NBN also, benzyl also. So benzyl can be easily removed by hydrogen palladium charcoal condition. Okay, so it can reduce this imine as well as it can deprotect this benzyl group. So we are using the same protecting group, so that we can, so that we can get both reduced product. Okay, so we'll get this primary amine. So this is our last conversion we can easily get. Okay, so we'll stop today. So thank you for attending. So I'll stop today. Okay, thank you. So have a good time and we'll meet in next week, right?